This PowerPoint presentation is from Chapter 14, Acid-Base Equilibria. Specifically, we'll be talking about Section 14.4 on the hydrolysis of salt solutions. In this tutorial, we will learn how to predict whether a solution of a salt will be acidic, basic, or neutral. Before watching this video, make sure that you have completed the reading guides for Section 14.4. Also, have your copy of the Chapter 14 handouts ready so that we can take notes as we work through this section. A salt is an ionic compound and is a strong electrolyte, although not necessarily very soluble. An example of an ionic compound is sodium carbonate. When sodium carbonate is added to water, it dissolves and dissociates into sodium ions and carbonate ions according to this equation. That means that the sodium ions separate from the carbonate ions in solution. Since sodium carbonate is a strong electrolyte, the reaction is written with a single arrow, indicating that the reaction goes to completion. What will be the pH of an aqueous solution of sodium carbonate? To determine the pH of a solution, you have to assess whether any of the species present in the solution can act as an acid or a base. In this case, our solution contains sodium ions and carbonate ions. The sodium ions do not react with water, but we've already seen that carbonate is a weak base. Since carbonate ions act as a base, we expect the solution to be basic. When looking at a salt solution, you need to be able to determine what kinds of ions will act as acids and what kinds of ions will act as bases. Salts are made up of anions, negative ions, and cations, positive ions. Some anions act as bases, some act as acids, and some can do both. The conjugate bases of weak acids are weak bases. The conjugate acids of weak bases are weak acids. This table shows acids and their conjugate bases. We're talking about, in this section, the weak acids and bases. An example of an anion that is a base is fluoride. An example of an anion that is an acid is hydrogen sulfate. An example of an ion that is both is hydrogen carbonate. Cations can act as acids. There are two kinds of cations that we need to consider. First of all, the conjugate acids of weak bases can act as acids. For example, the ammonium ion is an acid because it is the conjugate acid of the weak base ammonia. Small, highly charged metal cations can also act as acids. For example, the aluminum 3+ cation. At first glance, metal cations don't seem to be acidic because they don't appear to have any protons that they can donate. However, some metal cations don't exist in water as isolated ions. They form complex ions with water molecules. An example is the aluminum complex ion shown. The aluminum cation forms bonds to 6 water molecules. Because the water molecules use some of their electron density to form bonds to the aluminum cation, their oxygen-hydrogen bonds are correspondingly weaker. This means that the bonded water molecules can donate one of their protons to free water molecules in solution. The equation for this reaction is shown. Notice the production of the hydronium ion, indicating that the solution will be acidic. What kind of metal cations do this? Transition metal cations that have a charge greater or equal to 2+, or main group metal cations that have a charge greater than 2+, and then we also have an additional example of lead 2+ cations. Usually, a metal cation will form bonds to either 2, 4, or 6 water molecules. If not otherwise stated, assume 6 water molecules. Notice the highlighted examples of metal cations on this slide and their corresponding Ka values. Let's do an example showing how a metal cation can act as an acid. Consider the copper 2+ ion in water. Since copper 2+ is a transition metal cation with a charge greater than or equal to 2+, it will form a complex ion with water. This reaction is written as follows. This reaction shows the formation of the complex ion. This is not the reaction that shows how this acts as an acid. It is this complex ion that can undergo an acid reaction. The complex ion can react with water and donate one of its protons to the water molecule in the following reaction. Notice that we use a double-headed arrow for this equilibrium. Notice also that the products of the reaction include the hydronium ion, again indicating that the solution will be acidic. Notice how the formula of the product copper complex is shown. Since one water molecule from the original complex donated its proton, there are 5 water molecules remaining that are attached to the copper, and the 6th water molecule is now an OH ion. Since the original complex had a charge of 2+ and it's lost a proton, the new complex has only a charge of +1. The Ka for this reaction is given in our acid-base table as having a value of 3 × 10⁻⁸, indicating that it is a weak acid. So far, we've seen examples of ions that act as acids or bases or both. However, some ions don't hydrolyze or react with water at all. Examples include ions that are conjugates of strong acids or bases. For example, chloride. Chloride ions will not alter the pH of a solution. Metal cations that do not form strong bonds to water will also not hydrolyze water. Transition metal cations with a +1 charge, like copper +1, will not cause a solution to be acidic. Main group metal cations with a +1 or a +2 charge, like sodium ions or calcium ions, will also not affect the pH of the solution. Therefore, a solution of sodium chloride, for example, is expected to be neutral because neither ion hydrolyzes water. Let's summarize the steps to take to determine whether a solution containing ions from salts will be acidic, basic, or neutral. First, write down all major species present and evaluate their acid-base character. You will need to be able to recognize common weak acids and bases from the above tables. In our opening example involving sodium carbonate, what ions were present? Sodium carbonate contains sodium ions and carbonate ions. We've seen on previous slides that the sodium ion does not hydrolyze water, but that the carbonate ion is basic. This means that a solution of sodium carbonate will be basic because the carbonate ion is basic. What if there is more than one ion that reacts with water? If more than one acid or base is present, the species with the largest K value will dominate. For example, a solution of iron 3 fluoride will contain iron 3 plus cations and fluoride anions. The iron 3 plus is expected to act as an acid and has a Ka value of 6.3 times 10 to the minus 3. The fluoride ion is expected to act as a base and has a Kb of 2.9 times 10 to the minus 11. Which one wins? It turns out that the species with the larger K value will dominate. In this case, the Ka of the iron 3 plus is a larger number than the Kb of the fluoride, so the solution will be acidic overall. It can also happen that a given ion is amphoteric or amphiprotic, which means it can act as either an acid or a base. What do we do then? If a species is amphiprotic or amphoteric, the reaction with a larger K value will dominate. For example, the hydrogen phosphate ion is amphoteric. If we look at the K values, the Ka for hydrogen phosphate is 4.2 times 10 to the minus 13. Its Kb is 1.6 times 10 to the minus 7. Since the Kb is a larger number than the Ka, the solution will be basic overall because the hydrogen phosphate ion is stronger as a base than it is as an acid, and it will act as a base in solution. Make sure that you're able to calculate Kb values from the correct Ka values. Take a moment to convince yourself that the Kb value of the hydrogen phosphate ion shown is correct. Remember that it would be calculated from Kw divided by the Ka of its conjugate acid, so of the H2PO4 minus ion. Let's try an example. Will a solution of calcium nitrite be acidic, basic, or neutral? First, what ions will be present in the solution? Calcium nitrite will have calcium ions and nitrite ions. Is calcium expected to react with water? The calcium ion is a main group metal cation with a charge of +2. It's not expected to react with water because it's a main group metal cation, but the charge is not greater than 2. Is nitrite expected to react with water? Nitrite is a weak base. Therefore, it is expected to act as a base in water. Since we have only one ion that either has acid or base properties, and that ion acts as a base, we expect the solution to be basic overall. In this presentation, we've shown how to determine whether a salt solution will be acidic, basic, or neutral by evaluating the acid-base character of the ions involved. After watching this video, you should be ready to work on group problem number 11 from the Chapter 14 group packet.